Hello and welcome back to the Tin Barn. I'm Pragmatic Lee, and as I'm sure you figured out by that intro video, today's video is going to be about CNCing the X-axis on my surface grinder using a NEMA 23 stepper motor and a Raspberry Pi computer. Now, if you've been with the channel long, you know that my most recent videos have been dealing with that. The first of those videos was showing the ability to use a Raspberry Pi computer to not only change the direction of a stepper motor, but also send steps to it or pulses to it to cause it to step X number of steps in each direction. Here's a short little clip from that video. Then in the next video, I wanted to demonstrate another feature of the Raspberry Pi of being able to not only send a command out to change the direction or to send a pulse out, the Raspberry Pi could also take input in. Example being a limit switch, being able to detect when a limit switch was pressed, change directions, and go until it presses a limit switch on the other side. Here's a short little clip of that. And then finally, in the last video, what I did was show making these bumpers to go in here, and the limit switch is mounted to the center. Here's a bit of an unpublished clip. I think I did put it on Facebook, but hadn't put it on YouTube yet. But just a clip of that in action. Okay, to get to this point has been a learning experience for me, to say the least. This is my absolute first experience with a stepper motor. It's not my first experience with a Raspberry Pi, but it is the first time I've ever tried to control an external device with a Raspberry Pi. Now, in the previous videos, several folks ask how you connect a Raspberry Pi to the computer. Let me try to make this as simple and straightforward as I can. The Raspberry Pi is the computer. It's approximately the size of a pack of cigarettes. This one right here happens to be a Raspberry Pi 4. What I'm using for this project is a Raspberry Pi 3. But it is a complete standalone computer. You can surf the internet with it. You can do word processing, spreadsheets, email. Anything that you can do on a desktop computer, you can do with this. They range in price anywhere from, I don't know, $45 maybe up to $100. The Raspberry Pi 5 has just been announced this week. But the Raspberry Pi is the computer. We're using the Python programming language to write the code for the Pi to control these items. Now, what's involved here, as was stated in those previous videos, there's the Raspberry Pi, there's the stepper motor. Up under this down here is a controller for the stepper motor and a power supply for that controller. All those components were listed in that first video I did entitled something to the effect of controlling large stepper motors with a Raspberry Pi. Now I want to get set up and show you some of the trials and some of the failures, because in this project I had a lot more failures than I had successes. But in the end, as you saw in that introductory clip, we got them worked out, and got them worked out with the help of some of you guys as viewers. So I'm going to get set up and show you the first iteration that I tried that was a failure. Now, being very naive concerning stepper motors and controlling them with an external device such as a Raspberry Pi. I thought I could simply write a program that would send a number of pulses to the stepper motor, let's say 600 pulses, and it would move to a point, and then we would stop after that 600 pulses, reverse direction, and send 600 pulses back in the other direction. And I thought that was going to be all there was to it. But let me show you what I found when I wrote that program. What I've got is a piece of paper taped down to the mag chuck here. I've got a straight line drawn on it, and I've got a vertical line on the spindle. I'm going to set this machining square up so that it's lined up with this line on the paper down here, and also lined up with this vertical line on the spindle. So that's going to be our starting point. Now I'm going to run a program that it's going to loop 50 times, sending 600 pulses out in one direction, change directions, and come back. Again, we're going to do that 50 times, and we're going to see, well, I'll show you the result. All right, there's our 50 steps. Now, I'm going to set the square back up here, lined up with this line down here, just like we did to start with. And can you see what has happened on the camera? Here's our vertical line right here that we started with. And in just 50 rounds, we've lost almost 3/4 of an inch. In other words, everything has shifted. Now I want to show you that code right quick and see if you can determine what is wrong there. This obviously is not going to work. If we put a piece up here and we run, instead of just 50 rounds back and forth, we become closer to running 200 or 300. We will be completely off of our workpiece before we could ever finish the grinding. So let's take a look at the code of the program that I was running for this. Okay, here's the code that was used in that first demo. Now all this code up at the top up here is defining some variables, setting up the mode, setting up the pins. All that was discussed in detail in the previous video on, I think it was entitled Controlling Large Stepper Motors with a Raspberry Pi. But the part of this that's most relevant to what we're doing right now, or what we want to look at, is this try loop right here. Now, if you recall from that previous video, I pointed out that the only reason it shouldn't be able to run this code is if a Control-C was typed on the keyboard. If it sees a Control-C, it'll drop down to this loop down, or this exception down here, as a keyboard interrupt, print out, clean up the pins, and exit the program. Right here is what we want to look at. This little demo program is going to run 50 rounds, starting at 0 through 49. So as long as this counter is less than 50, it's going to run this while loop right here. Anything that's indented from the while. So it'll print on the screen just a little statement of the round, steps needed, and the direction. The direction we set up here before we fell in, or before we got into this try while loop, we set the direction to the clockwise direction and sent that information out to the direction pin. So now we're going to say for X in the range of the number of steps. And we've set up here we want to do 600 steps. So these three lines right here are a pulse. So we'll send to the pulse pin the high signal. We'll set it high, sleep for 1/1000th of a second, and then set it low. That's simply a pulse to that stepper motor that says pulse or increment 1 step. Then we'll sleep for 1.5 thousandths and repeat this for loop right here until we get up to our 600 steps. Once we get through the 600 steps, the program will make a decision. It basically says if the direction is currently clockwise direction, then change the direction to counterclockwise. Else, if the direction is counterclockwise, change the direction to clockwise. That's simply toggling the direction variable between clockwise and counterclockwise. And then we output that to the direction pin. Now remember, it's going to stay in this indented while loop right here until Control C is encountered. If Control C is encountered, it will fall down to here. When it expires the number of rounds, in other words, when this counter gets up to 50, it will not run this while loop anymore and fall out to simply put on the screen, clean it up, and clean up the pins, and the program ends. Now, we don't see any indication right here of why it's not coming back to the same starting point every time, or it's not going out the full 600 steps. We're telling it to go in whatever direction set to, go the exact same number of steps. So why aren't we coming back to that same starting point? Okay, as to the cause of why we're not getting back to the same starting point each time, losing a little bit on every round, we'll get back to that a little bit later. As I said earlier, this is my first experience with a stepper motor, and I really didn't know what to look for. So I decided I'd go that different route of using the bumpers. Now I'm going to bring the camera back around here to the bumpers and talk about them just a little bit, and then show you what happened or why they didn't work. Again, this video is about not only the success of getting it done, but the couple of major failures I went through to get to that point. In the video where I showed making these pins for the bumpers, several people commented that, Lee, you can get more space out of your table if you'll turn these brackets around. And that is true. If I flip them around and put the pin spring out this way, I could get more width on there. But the idea of these bumpers was to be able to adjust the position of them based on the width of the material I had up here. If I had a 3-inch piece that I was grinding, there's no need of running the full length of the table, the full 12 inches of the table, if I'm only grinding about 3 inches. If I was to flip these over and put the pin out this way, it would be practically impossible to get to this socket head cap screw on the inside. So I was willing to sacrifice about a 1/2 inch. I could bring this out based on the piece of the size of the material. I could bring them out to here and maybe lose 1 inch of that 12-inch chuck. But all of that was pretty much mute to begin with, or after I discovered what we're going to see here. you'll see right here this red button. Yes, that's a panic button, a stop button. I originally had just a toggle switch here to turn the power supply on down here that powers the controller. And because when power is on, you can't move this table. It's locked then. That's one of the things about a stepper motor. It holds its position as well. However, when you remove power, you can adjust it back and forth. Say right there is about the center of the table. And I'll get these two bumpers about centered around that. Something like that. Okay, so that's the purpose of this. And instead of just having the toggle switch there, I said, you know, what the heck, why not put a panic button there so if something does go wrong, all I've got to do is slap it and everything stops and I don't crash anything. All right, I'm going to run a program now. The table is going to move in one direction until this bumper hits this switch. When it hits that switch, it will stop. Reverse directions and go in the opposite direction until this bumper hits that switch. Watch what happens. Now that's working as good as anybody could ask for. I was right ready to do up all the cables, tie them in place, and call this project finished until I did the very necessary part of grinding. Watch what happens when I turn the spindle on up here. Turn it on now. Spindle spinning now. The switches have gone crazy. I'll turn it off. As the motor winds down, goes back to normal operation. I discovered that late one afternoon, just before I was ready to go back in the house. And I literally laid in bed about half the night trying to figure out what in the world was happening here. And I convinced myself enough so that I could finally go to sleep that it was electrical interference. So I come back out here the next morning, I unplugged the power supply to the regular, or to the stepper, to the driver is the word I'm looking for. The power supply, the monitor up here, and the Raspberry Pi, I plugged all three of them in on an entirely different circuit. Completely off the circuit that the VFD for this is on. As a matter of fact, I made an extra point to be sure it was on a different leg of the 220 coming out here to the 10 barn. Didn't make any difference whatsoever. Still got the same interference. Then I noticed the interference was coming as the motor spun up. When I applied electricity, it didn't immediately go to messing up the contact, the switches. It's not this switch here that's being interfered with. It's the pins on the Raspberry Pi. I did a little reading on them, and they are extremely sensitive. So what I decided to do was move all the Raspberry Pi, all that stuff, as long as my cables would reach. Got it about 4, maybe 5 foot away from the spindle motor. Same thing. Got the same interference. So I'm just, I'm literally at a loss of what to do. I've tried going a set number of steps, in same amount of steps in both directions, and we just saw where after no more than 50 rounds I had lost 3/4 of an inch. I tried the switches here with the bumpers. Looked like it was going to work fine until I'm guessing it was a magnetic interference from the motor spinning. I'll show you the code right now on how these switches work. And from that, you might be able to use that in another project. Before I do that though, in that video where I was making these pins, I mentioned the fact about it not coming back to the same point every time, or after a set number of rounds. And several people commented on that and told me what was wrong. And we're going to get to that after we look at this code. All right, here's the code for our second demo that we're looking at. And this is very, very similar to the first code we saw, with the exception of, in addition to pins 20 and 21, which was our direction pin and pulse pin, we've got two more pins, a pin 23 and a pin 24, and we are setting those up as input pins. 20 and 21, we were sending a signal to it. 20, the direction pin, we were either setting it to 0 or 1, 0 being clockwise, 1 being counterclockwise. And then pin 21 was our pulse pin that we were sending pulses out to. We set up two more pins that are tied to that limit switch that's in the center of our surface grinder, that the bumpers that we saw in a previous video, we saw making in a previous video, those bumpers hit those limit switches, and they're on pins 23 and 24. Now we're not concerned about the number of steps here. We're going to continue this try loop right here until we encounter a Control C. In other words, it's going to run forever until somebody types on the keyboard Control C, and then it falls out and cleans up. So this, first off, we're simply going to print on the screen what direction we're in, and we've set the direction to 0 to begin with, clockwise, and we've sent that out to pin 20. Now, while true, and as I said in previous video, true is always true. That's like saying while 1 equals 1. So this loop is going to run forever until Control C is encountered. So we'll send the pulse out. Remember, our pulse pin was 21. We'll set it high, sleep for 1/1000th of a second, and set it low. Now we're going to continue to do that in this while loop right here until, after each pulse, we're going to check pin 23 and 24, our limit switches. And if either one of them is equal to 1, which means that that limit switch was pushed. If it was set to, if either one of them was set to 1, in other words pushed, we don't care which one, either one of them, we're going to immediately set the output pin 21 back to low. Just take any power off of that pin. Now we're going to toggle the direction. If the direction was equal to 0, then change it to 1. Else, if the direction was equal to 1, set it to 0. We'll print on the screen the new direction, sleep for 1/4 of a second, output that direction. The only purpose of this sleep here is just in case the code needs to, or the computer needs to catch up with the code. This could be much smaller right here, but we'll send out that new direction. Now we don't want to immediately go back and start sending pulses here, because that table has bumped into that limit switch. And we need to get off that limit switch before we go through this loop of testing if either one of them is set high. So once we change directions, we'll go in a simple range of 50 steps now. That was just an arbitrary number I come up with just to be sure that we have backed off the limit switch before proceeding. So we'll send a high and low for 50 times, sleeping just a little bit, 0.02 of a second. And again, this is just given a chance for the stepper motor to back up in that new direction just enough to get off of that switch over here. And then we'll put the message on here that we're sending the pulses, sleep for our delay, which was 0.02, come back around and start sending these pulses back and forth again until one of those switches is bumped. See, what happens as it sends these pulses, if both of these switches are 0, it doesn't execute any of this if loop right here and comes right down to our delay and then comes back to sending pulses again. I bumped the wrong key there and deleted some stuff. So again, it's going to do this. If this statement is not true, it ignores this if statement, everything that's indented on that if, sleeps for our delay, comes back and sends another pulse, on and on and on, until it encounters one of these switches being set high. When it encounters that, it toggles the direction, backs off the switch just a little bit, 50 steps, and then goes back into the same routine again. So again, this code was working ideal except for the interference, magnetic interference, I'm guessing. When we encountered that from the motor spinning, then these switches were artificially being set high, I guess is the best term. Okay, if you've stuck with me this long, then you're obviously interested in the outcome of this video or outcome of this project. Now, I've removed the limit switches here and the bumpers, and we're back to the setup from that first demo. I have, using the same piece of paper, I've got the square standing here, and I've got it lined up with this vertical mark here on the spindle. That's going to be our starting point, just like it was in that first video. We'll pull this off a little bit just so this bolt over here doesn't strike the square. We're going to run pretty much the same program that I did in that first demo with just a little bit of changes based on those comments on the bumper video. This is going to run 50 rounds, 50 loops, again, just like that first demo. And I will fast forward this or speed it up so you don't have to watch those 50 iterations in real time. Now as that's running, see if you can notice anything different in the way the table is moving. I'll leave it at normal speed for several rounds here. All right, let's speed it up now. All right, let's wind that back down and look at there. We're in the exact same spot again on that heavy vertical line. Let's take a minute and look at one more section of code and see why this works now. All right, now let's look at the code for the third demo we saw, the one that's actually working properly. Now, here was the first demo. We got steps, 600 rounds, the direction, and we're simply in this try loop again right here. sending pulses for the 600 steps. Notice our sleep time between each pulse is 1.5 thousandths. That number right there is what determines our speed. Now let's look over here at the third demo, the one that is working properly. All this up here is exactly the same. This is the same. But what we're doing, instead of one for loop that goes through the full range of steps, we're going to do 3 different for loops. This first for loop is in the range of the steps times 0.15, 15% of the steps. Now we're going to convert that to an integer, a whole number. The number of steps in these demos is a set amount, static amount. But in a live situation, those number of steps will be based on the length of the stroke that we need. And I'll get into that in a little bit more in the final demonstration. But we want to take 15% of the steps, and by calling this integer function, we're basically rounding it off to 0 decimal places. But an integer does not have any decimal places, so it's, in common terms, a whole number. So 15% of the steps as a whole number will send pulses, but instead of sleeping that 1.5 thousandths, we're going to sleep almost 4 times that, 3 times that amount. We're going to sleep for 4 thousandths of a second. In other words, we're going slower here for the first 15% of the range. Then we're going to, after we finish this 15% of the steps, we're going to fall down into this next for loop and do it for 70% of the steps. And again, making that a whole number. And here we're going to sleep our normal time, 1.5 thousandths. So slow, fast, and then the last 15% of the steps, just like this up here, we're going to slow back down again. So what is happening here, we were losing steps. It was like driving a car where you're sitting at a standstill and all of a sudden you hit the gas pedal and you spin your tires. The tires are turning, wheels are turning, but you're not moving. And that is what was happening over here in this first demo, where we started out at full speed. Remember, the lower this number, the faster it gets in this loop. And we were spinning our tires. Then when we got to the end of this, we were like slamming on the brakes and sliding. Our wheels have quit turning, but we're still moving. And this was the effect basically caused by this heavy table. Again, this table weighs, with the mag chuck on there, probably weighs, I'm going to say 80 to 100 pounds. And in this first demo, we were trying to go from a dead standstill to full speed instantly. And then we're trying to go from full speed to a stop instantly. And it was not happening. So what we're doing is taking 15% of whatever steps we've calculated. In these demos, that's a set number, 1600. We're taking 15% of them and doing it slow. Then we're doing 70% at our full speed. And then to slow down, we're doing 15% again. 70 plus 15 plus 15 is 100%. And after we've done these 3 different speed ranges here, we'll check our direction. If it was clockwise, we'll toggle it to counterclockwise. Else, if it was counterclockwise, we'll toggle it to clockwise, and we'll send that new direction out to the direction pin and loop back around and keep doing it. Come back to the beginning of this while loop, increment the rounds one time, do 15%, 70%, and 15%. All right, let's look one more time and see if you can notice it this time of how it will start out at a slow speed. Then you'll see it speed up a little bit to its normal speed and then slow back down. Reverse directions, start out slow, speed up, slow down before we stop. Now I'm going to hold the microphone down close to the stepper motor. We'll see if it picks up the difference in the sound of the motor between the slow speed and the higher or faster speed. Alright folks, I apologize again for this video being so long. I usually try to limit my videos 25 to 30 minutes, but this one has run way over, and I've still got right much material, or not a lot of material, but enough to warrant another video on how I implement those changes in the speed program and the entire process, how I implement that to work with a narrow piece or a wide piece or an extra wide piece. These demos we've been seeing, we were going a set amount of rounds back and forth on the chuck. We want to be able to verify that, or we want to be able to modify that value as we run the program based on whether we got a narrow piece of material, or maybe we got a piece a little wider, or even a little wider than that. So come back next week or next video, and I'll do one more in this series, or I got one more planned in this series on implementing the programs to actually work on the surface grinder. You guys take care, and I'll see you on that video.